Let's resume the talk, and I'm starting with the how power is outcoupled with a device under test from Magnetron. There are two way of coupling RFR. One is loop antenna coupling, and second is waveguide coupling. Here, first, I'm showing you the loop antenna coupling. Here is the window. It's a coaxial line. This loop antenna couples the RF to the coaxial line, and this alumina disc preserves the vacuum inside the magnetron. The size of the coupling loop and its orientation affect the magnitude of the coupling. Sometimes the coupling loop is located above the inductive region of anode in the end space region of the magnetron. This kind of coupling is called hollow loop coupling. Now, the second type of the coupling is waveguide coupling. This coupling is used for very high power. RF coupling, when your magnetron is at high power, this sort of coupling. Here, a rigid waveguide is shown. If you have other view of this waveguide, as you have seen in the case of this coaxial cable, this sort of coupling slot is RF is directly coupled to the waveguide, to this rigid whole waveguide, and then this RF is carried out to the device under test. The cross section of rigid hole is shown here. The waveguide portion is called each section of the obvious reason. The rigid waveguide section is approximately a quarter wave in length and has the appropriate impedance to optimize the coupling. Although these transitions have been called matching sections, they do not provide a match in the sense having no reflected RF path. When we match the impedance, there are one disadvantage is that if power is reflected back, it goes directly into the device because its impedance is matched.
How do they calculate the impedances?
Impedance of magnetron is calculated. So HV applied divided by current. For example, if you have a E2V magnetron 5193, its maximum HV is 45 kilovolt and current is 120, and its impedance will be around 400 plus minus. The exact impedance is difficult to measure. It is always much smaller than the coaxial line or waveguide output from the magnetron. Hence, some form of impedance matching transfer must be used. A conventional method with coaxial output is to use a linear trapped center conductor to obtain both impedances and geometric transition. Actually, as I have given the example of MG5193, whenever you use it for lower power, you have to take care of its impedance. Doesn't matter whatever you are using for the power. For example, you are driving it at 40 kilovolts, then you know that the quoted impedance is 400 plus minus. So you calculate the current and the same amount of current applied that such that the impedance is always the same way. Now, next is the cathode heater operation. We have already discussed that initially cathode is heated, it emits electrons, and as the average power increases, a back bombardment of electrons to the cathode also increases, which cause the heating and secondary emission of electrons. Secondary emission of electrons is not a problem in this case because the purpose of cathode is to emit the electrons, whether they are primary or secondary. But overheating can melt this cathode. To deal that overheating, we have to cut off our own heating, the filament heating we are providing externally. Now, the performance here, IV characteristics of a typical magnetron are shown. The voltage current characteristics of normally is the optimum operating condition as indicated by this particular 26 kV and 30 ampere dot here. This is because the impedance of the magnetron must be matched with the impedance of your device. And the other case where I have already quoted that for other magnetron, it's 45 kV and 120 ampere. When anode voltage is varied, current changes, and so power output, and to some extent the efficiency of the magnetron also changes. As current changes, the electronic impedance varies, which affect the resonant frequency of the resonator, and so the frequency of oscillation changes. Figure below shows a data sheet of MG5193 Megatron, which is operated at, which has maximum RF power 2.5 megawatt, and it is fabricated by E2B, and its optimum voltage and current is given here. And this spec sheet tells that if we change the voltage, we must be changing the anode current as well. And the RF power also changes. For optimum voltages and currents, the RF power is almost 2.6 megawatt. When we decrease the voltage, then to have the same impedance, we have to decrease the current, and the output power also decreases. Not output power decreases, but the frequency also shifts. Here, the shift in frequency in megahertz is shown. From if we decrease 45 to 40, the frequency will be decreased almost 0.7 megahertz. Now, another concept is frequency pushing. What it means? The change in frequency with current is called frequency pushing. Current mean if you change your HV and current of the magnetron, its frequency also changes, and this phenomena is called frequency pushing. The resonant frequency of the vane is determined by its dimensions as well as its reactive effect of electrons. As this current is decreased, electron current or spoke current, which is moving inside, then reactive effect of these charges on the capacitance of the cavity also changes, which cause the change in the frequency. The pushing figure is usually expressed in megahertz per ampere and is represented by the slope of the frequency versus the current curve plotted for the particular magnetron type. The slope is not as constant, so it is necessary to specify the range of current over which this applies. Power output is proportional to current. The pushing figure at current level, well below the normal operating point, is usually unimportant because the power output at these current levels is low. The importance of a low pushing figure is that the pushing figure will determine intra-pulse frequency modulation and thereby will affect the spectral quality of the transmission line. The next is frequency pulling. Now, if somehow we do not fix the proper voltage and current, then impedance of the magnetron is changed. And definitely, if the impedance is changed, the frequency also changes. The output frequency of the magnetron also changes. And this phenomena is called frequency pulling. If the magnetron is operated into the load, the impedance of which varies with time, then the frequency and power will vary with time. As an example, a rotating antenna will usually present a varying impedance to a magnetron, so frequency and power will vary with antenna position. To overcome this sort of problem, we can use ferrite isolators, which can significantly reduce this variation. The resulting variation in frequency with change in load condition is called frequency pulling. During design of a magnetron, the pulling of the coupling of the output waveguide to the resonator structure is selected to optimize certain performance parameters. Strong coupling increases output power, but output power and efficiency, but also increases jitter and sensitivity to the change to the load mismatch. Usually, the coupling is chosen to obtain the best compromise between efficiency and stability. Here, I have discussed this figure. Now, there is a thermal drift. How a change in temperature of the magnetron changes the frequency, resonant frequency of the magnetron. When we start the magnetron initially, it needs some time which is called LV conditioning, mostly 15 to 20 minutes. In that time, it attains the almost steady temperature. When high voltage is first applied to a magnetron, the tips of the anode vanes begin to heat due to electron bombardment. During the time required for each part of the magnetron to stabilize at its normal operating temperature, the output frequency of the magnetron will drift. And once this temperature is normalized, the drift in the frequency stops. Generally, the maximum drift occurs during the first few minutes after turn on and slowly approaches to the equilibrium. In low frequency magnetrons, the RF circuit elements are relatively massive, and the time required to reach this thermal equilibrium may be much higher, up to 1 hour. At X band, where the size of a magnetron is small, and the time to reach equilibrium is a few minutes, sorry. Here in this graph, it is shown that for different temperatures of frequency drifts from 1.25 gigahertz to 1.35 gigahertz. It's the duplicate. Okay. Each type is usually designed for a particular application, and small differences in internal configuration can produce large differences in the thermal drift curves. It should be noted that a thermal drift effect will also occur whenever the input power to the magnetron is changed. And a change in ambient current also changes the frequency of output frequency of the magnetron. The compensation techniques are used to offset these temperature effects. A bimetallic disc element can be used in the cavity of coaxial magnetron to correct the cavity expansion. Similarly, bimetallic elements can be used in the drive linkage to the tuner to compensate for temperature-induced frequency differences. Now we come to the applications of a magnetron. The low energy accelerators use magnetron as a RF source. So all low energy electron accelerators from like to say 3 to 4 MeV to 15 MeV all use magnetron as a RF source. And those accelerators can be used in medical, in R&D, in industry, and in many other applications. So the maximum of use these low power accelerator is in medicine, and the second highest use is in industry. So if we talk about conventional magnetrons in medical, RF power 2.6 to 3.1 megawatt and energy from 3 to 15 MeV with average RF power from 4 to 8 kilowatt for oncology. Here, this magnetron is used in a linear accelerator, which is used for oncology, and power of these magnetrons are from 2.6 to 3.1 megawatt, and the average power is 4 to 8 kilowatt. These low power magnetrons are also used for the simulators. These simulators are used to diagnose the cancer. Low power Linux are used to diagnose the cancerous part of the body, and then these high power, comparatively high power Linux are used to treat those parts. And why they are used here? Because they are small in size. They are mounted on the gantry, and we have a compact gantry. Gantry is our device which rotate around the patient and deliver the dose from different angles to a particular part of the body, so that the other healthy cells are not affected. The efficiency of these magnetrons are almost 60 or over 60. These are also can be used for high average power. For high average power Linux, where flash radiography is used. In border security cargo scanning with single or dual energy ranging from 3 to 9 MeV, Linux are these magnetrons are used. At airports, cargo and luggage scanning is used by done by these low energy magnet Linux, which use the magnetrons. In defense, these magnetrons are used in radars for NDT, non-destructive testing. For example, if a small missile, you want to see the uniformity of its fuel or any crack in its body, you can use LINEC 3 to 9 MeV LINEC, and that LINEC is again powered by magnetrons.
I was thinking about how the temperature changes the frequency of the magnetron. You said that electrons collide with the vein
Emit.
and when the vein gets heated, do you mean that it changes the conductivity or
No,
what?
the frequency of a resonator depends upon its size. It's slightly heated,
Oh,
its energy is changed. The change in energy per degree is almost 5 kilowatt kilohertz. If you change the temperature of a cavity by 10 degree, so almost 50 kilohertz frequency, the change in frequency will occur.
because the size is changing.
Size is changing due to expansion and contraction. Okay. Similarly, these magnetrons are used in heating in industry. There are not many processes like cable sleeve processing. Sleeves on the cable are heated and they very strongly stuck to the conductor. And so there are not many applications. At the end, I am thankful to organizers, especially Dr. Arkan. I am also thankful to Dr. Slatin and other organizers of the school. I'm also thankful to Dr. Tariq Elijah Sahab for guidance and support. It was a wonderful experience for me to be the part of this school, and I got an opportunity to learn, and I learned a lot from this school. My best wishes for the organizers and all the participants.
Thank you. And that you had you here, all the way from Pakistan. We appreciate, and also we congratulate you for the Pakistan Independence Day today.
Thank you, sir.
Just one comment. Nowadays, for medical application, Electron is mainly used.
Yeah.
So what are the merits and demerits between the two, magnetron and Electron?
Magnetron is a small, actually, for oncology treatment, the maximum cases are almost 80% cases are treated by 6 MeV. For 6 MeV Linux, always magnetron is used.
Nowadays, they are going
Yeah.
to 15 MeV and
15, 20, and maybe e-beam and so on. In that cases, definitely they use Electron.
So higher energies to prefer.
Yeah. But to old,
Old ones are on magnetron.
even for 15 MeV, up to 15
Yeah,
MeV.
Some companies, they just traditionally use magnetron.
Yeah. Yes, please.
The thermal drift happens because of the aging, or no? From the beginning, we have this expansion.
What?
The thermal drift.
Yeah, I have already explained that when temperature increases, cavity expands.
It's because of the aging, or no? From the beginning, we have this expansion.
No, we give some time to get the cavity at an equilibrium temperature. Sometimes, somehow, if ambient temperature is changed, our cooling channel is not properly working, then cavity can expand and frequency can change.
We are in a vacuum, but the cooling system
Is outside.
affected by that.
Yeah, cooling system is outside. If you see the first slide, I'm sorry. This one. This part where you have cathode, you need to heat it. You never like to cool it. But this outer part, you want that its temperature remains constant during the operation. If its temperature increases, the size of these cavities increases and frequency decreases.
Does it mean that if the temperature of the environment changes, frequency also changes? for the
No,
magnetron?
you have a good cooling channel around it. You always
Cooling.
cool it.
Yeah,
You
cool it.
try your level best to retain the temperature of the structure. Constant temperature of the structure.
structures.
Thank you.